Okay, so welcome to an exploration of valkey-bundle. It's a comprehensive solution for building modern low-latency applications. Raise your hand if your company has any Gen AI strategy or told you to jump on the bandwagon. Yeah? Keep it up, keep it up. I want to know. I do have a, yeah, there you go. We all are in the Gen AI bandwagon. But raise your hand if you have any concerns about cost. No? Nobody, yeah. We all do, right? Like, Gen AI, as good as it is, there's some caveats, latency and cost. So we're going to see how we can take advantage of Valkey to solve that problem. All right, let me introduce myself. My name is Roberto Luna Rojas, or just Robert. I'm a senior developer advocate for Valkey, and I'm really glad to be here with you today to talk to you about the valkey-bundle, which is a comprehensive solution to build real-time applications with extending Valkey core with a set of different modules. Those are JSON. Who here uses JSON? Pretty much everyone, right? That's kind of the quintessential data model or format that everybody uses, especially for APIs. Bloom filters is a probabilistic data structure that allows us to maintain cardinality and keep a very accurate count of unique elements without sacrificing memory usage, and we can handle the error rates, right? So we're going to go through those. There's also vector similarity search, which is what is going to enable us to power those Gen AI applications. And finally, LDAP, which we're not going to go into too many details. There's a session for that. So we're going to go through an architecture for the application, but first, let's see the demo. Okay. There we go. All right, so we have this browser where we have a Valkey application. It's a small demo that somebody from GCP created, and then I extended it. So there's a user. And this is a person that is an indoor geek, right? So that's kind of the name of the person, and then there's some personality, it's a bio, that we will see the details. But I'm going to open up a different browser with a different user. This is an outdoor fanatic. So there's two different persons, and we're going to make the same search. And in this case, the indoor person gets results for headphones. And as you can see, these are more like gaming-oriented, kind of high-quality headphones. And there's the outdoor person. We do the same search, and then we get different results for the exact same search term. And these are more like tailored to outdoor person who is likes to go and run or hiking or things like that, right? More rugged devices. And I also have this little icon that is showing me that the person has seen this product, right? There's also a description that is personalized and tailored for this particular user. So it says, inspired by other fanatics, enthusiastic admiration, whatever, right? So this description of the product, it's made for this particular person. Similarly, we have the same for the indoor one. So this is kind of the idea. In this case, I'm going to go to this product, and I already have a description preloaded for me. We're going to see the details about how that's done. But if I go to this product on the other person, we see that we do not have the description. So that takes a little bit of a while, right? This is where the LLMs are, as good as they are, they will always spend some time. In this case, it took probably a couple seconds, and it's running locally. So I have a tiny llama running behind the scenes. So we're going to go how this application is structured. But first, I'm going to open up for any questions that you may have about it. No? Do we keep it to the end? Right, let's go back to the slides. So, okay, right. So this is an AI power personalization engine that is powered by Tiny Llama, like I said. This application supports Google Gemini or AWS Bedrock with Nova Pro. And there's different embedding systems as well. There's a hybrid search support that is supported by the vector similarity search module from the valkey-bundle. And we're using Bloom filters to keep track of the products that the user has seen and deliver those real-time recommendations and the high-performance caching by using the core data structures from valkey. This is the way the application is built. It's a Flask app, very simple Python app. We're using also the built-in session storage, which uses valkey core behind the scenes. And we have the different modules and the backend. Like I said, we're not going to be using, or we're going to go into the details of LDAP. There's a whole session at, I believe, 145 that the folks from Percona are going to go into the details. So for now, no authentication. That's not a good practice. Always use TLS. Always have different authentication mechanisms for the data security. So, okay, the first component, we have products, right? This is an e-commerce application, so we have a catalog of products. In this case, we could be using whether valkey hashes or valkey JSON. In this particular choice, we're using hashes, so we can have a mix of both. And this is how they look like. So we have a Python example where we have the product ID, a name, brand, etc. And very importantly, we have the embedding, right? That's the detail that is going to allow us to provide the vector similarity search. And we're going to see what that means. So the hashes are extremely memory efficient. They're optimized for storing objects that have a schema-like. So essentially in a key, you can have up to 4 billion items, actually 2 to the 48th. So it's a lot more. Key value pairs, and they do have extreme performance, right? So by getting an item, you get that in an O1 operation, time complexity. You can think about it a little bit of a structured data or semi-structured data. This is where we go back to the demo. Give me 1 second. The slides are too small, so let's go back to the actual console and see how we can use it. So I have an example of a product here. That's the same structure that we had in the, in the slide. And we're going to go to the valkey CLI. All right, so we have a product with all its key value pairs, right? So we want to go and get the details. We can simply use the hgetAll command, get all the details. If we want to do go and extract only one item at a time, we will go and get, for example, the hget and the name, for example. Right? Fairly straightforward. This is the response, the same response that we're getting in the CLI. The main feature is that it's extremely flexible, super efficient, and this is probably the most common use case for product catalogs, session stores, pretty much, yeah, that's it. And we can get as many items as we want at the same time. Now, the valkey JSON allows us to have nested elements. I asked earlier if you were using JSON, right? So essentially, you will reach that when you have a structure that you need to nest elements within, and you want to go and access them in a particular order. And one of the cool things about bulky JSON is that you have the ability to use JSON path queries. So that means that you can go and fetch only a certain piece of the document without needing to fetch the whole thing. A very common thing that used to happen in the history of bulky and before that Redis is that people will serialize objects, store the whole thing, send it over the wire, and then whenever they needed it, they go and retrieve the item, send it back, make a change, send it back again to the server, right? So that's very wasteful in terms of speed, right? So that you have to get, let's say, 2K or up to 10K of data of objects whenever sometimes you just needed to alter one small item. The other one is the network. That's probably the most common use case for bulky performance issues. Clogging the network is so common. We've seen it all the time. And a great way to solve it is by taking advantage of the built-in JSON functionality. So in this case, I have a Python dictionary that I can simply go and save using the json.set command. Why? It's super flexible. It allows you to do atomic operations and those query capabilities that I mentioned about the JSON path. So again, I'm gonna go to the console. So this is not readable. Right, that's a JSON set command. We have a key, and we're pending things at the root, and then the whole document is just a string. For the first time, of course, we'll have to send it like that. But then whenever we do need to retrieve, we are very welcome to get the whole thing out. In this case, I'm just making it prettier to have the color coding from JQ. But of course, we can always go and perform other kinds of operations. In this case, I'm going to go and find the products that are between 100 and 200 in the list of the items in my purchase history. So I have two products, 456, that it was 123, and then 789, that is 234, right? So theoretically, I should be getting only the first item. So if I go, sorry. There you go. I have that by taking advantage of the JSON path functionality. Of course, there's no aggregations. It's very simple, but it does allow us to achieve what I was saying about reducing latency, improving performance in terms of network, and we can always go as well and make updates. So if I want to say, okay, I did actually like that product 789 a little bit better. It used to have a rating of 4, and then I suddenly say, no, I actually liked it more. Let's give it a 4.5. It has to be within quotes, sorry, from the CLI. Of course, I had to go to this bulky CLI. Oh, sorry. Okay, now we're good. Sorry about that. So if I go and get the JSON element, and just the particular product, we can see that it has been updated. So the whole point is we can go directly into just the items that we need to go and update, right? So it allows us to perform these atomic operations, and it is the point of it is that it's very, very efficient. Right, we saw this. Okay, let's get into the embeddings piece of this. Gonna go back to the mic. Okay, particularly for the users. Hello, can you hear me? Okay, right. So for the users, we have the embedding generation. So in this case, we're taking in the bio that is allowing us to understand what the user likes, as well as the purchase history. So based on that, we can create behavioral signals and preference indicators. We do this by creating a vector. We're going to see what that means in a second. Let's talk about Bloom filters a little bit. Who here knows what a Bloom filter or a probabilistic data structure is? Someone? You do? Yeah. Right. For the ones who do not know, probabilistic data structures are a functionality that allows us to store data with a certain margin of error. The caveat, or well, the benefit is the reduction of memory. So you can store millions or even billions of items and have a really good sense of cardinality or ownership. Let's say you have a username. You have a registration system. In that registration system, you need to check if a user has been registered or not, and that's a really way to know if it's there or not. For security reasons as well, like when you want to keep track of all the different IPs that the user has logged in from, and you want to prevent fraud. For networking as well, these are very common use cases. The way that it works, like on the diagram, there's a set that is a list or a vector of bits that are toggled, and every item goes through multiple hashes. So in this case, if we go to the X element that has the blue lines, it's toggling bit 2 and 7 and like 14, right? So that means that it's setting up those bits in order for us to track that item has been there. And then we do the same for Y and Z. So what happens whenever we do want to check, like, hey, have I seen X? With a very high percentage of accuracy, is going to tell me, like, yes, you have, yes, you may have, or you haven't. And there's no false positives. I'm sorry, false negatives. So for certain, you know that an item is not on the set. With a very high accuracy, you're going to say, yeah, it may be, and then you can move forward. You can say, okay, I'm going to double check on my backend database if I do have this user, for example. So that's what allows you to do, track extremely efficiently large collection of unique items. For our purpose, we're keeping track of the elements that we have seen. In this case, the products. Remember, on the demo, we were seeing like an item had those little eyes, like the emoji for the eyes. That means I have seen this product before. So let's just go back again. So in this case, I have the demo here. As you can see on the name, or actually the brand, I do not see those googly eyes. But if I refresh, I do see them. And then in this case, I have this product that I have seen before. So if I click on it, it remains there. If I go and perform the search, I do see that this product, as well as these other two, I have seen them before, right? So this is extremely useful, like I said, in security, as well as in ad tech. For marketing, for e-commerce, these are super helpful. Let's say in the case of the AI model that I was saying, you may want to decide if you do want to perform that personalized message on the first time or on the later time. Let's say somebody clicked on this product and it's probably like, if it's not a high-end product, you don't want to do a personalized view or description for that person. But if it is a product that you want to push forward, right, then you may want to decide, like, oh, yeah, they haven't seen it, let's go and generate it. Or if it's a tier 2 product, then you say, well, I'm only going to generate that personalized description on the second time, right? So that's when you can make a decision based on this. You can do bits as well. In this case, we're actually using numeric values. So you can always have a bit set and say the offset of the bits is going to toggle if I have seen this product or not. But it's very unlikely that a production database is going to have integers as the primary keys. right? I'm sorry. So let me explain a little bit about how the code works. Remember, they said you can, with Bloom filters, have a deterministic, well, a probabilistic way to say what the percentage of error rates that you're going to get and the items capacity. That's what you do with the reservation in this case. So you say, I want to create 1,000 items per user. I'm going to keep track of these many products, and then I want to have 1% error rate. And then we're just keeping track of them. It's super simple. As you can see, it's a O1 operation to add the item, in this case the product ID, to this Bloom key for the user. And then whenever you're checking, all you do is check with the exist command. So it's super simple. And then, of course, for the UI integration, we just iterate over the list of products. So just a summary, memory efficiency uses fewer memory than you will with a normal set, and it's extremely fast operations. We talked about the use cases, so now let's talk a little bit about vector similarity search. So the challenge is to find similar products that are relevant to the user or the search term that they're looking for. So it enables semantic search beyond what you can just do with tag-based or text-based search. So let's see some of the details. So first, who here knows what a vector is? I think I actually have the slides backwards. Not this, right? Not this vector, but he has the same concept, right? A vector, it's a quantity that has both magnitude and direction. In this case, whenever you're performing an embedding on unstructured data, like in this case it's text, right? So the products have description as well as the user has certain preferences. So what we do is take that text that in a structured format and create with the open source LLM a 384 dimension vector, right? So it's hard to visualize in physically, but that's how it works. So there's a lot of different dimensions on which the unstructured data becomes numeric values. And that's what enables us to find similar patterns or probably completely unrelated patterns that you didn't know about, right? So I like symphonic metal from the Nordics, right? So Sweden and Finland, but I like Taylor Swift as well. So whenever my favorite streaming music app gives me Ghost, I'm like, what's this? This is kind of a mix of both, right? So that's kind of the idea. Like, it takes all your different preferences and it allows you to have this with numeric backend. The way that this works on bulky search is by creating an index on existing data. So in this case, is the ft command that we're doing on products. And what we're doing is taking a prefix of the product data. So all of those items that we have in our catalog have a prefix of product, colon, and then the ID of the product. And we're taking separate fields, the brand, the search tag, the region, price, as well as the rating. And then we're doing a vector embedding of type HNSW. I'm going to go to that in a second, as the vector similarity search item that we're going to go for, right? This is the actual element on our hash, in this case, that we're going to use to perform those queries. In Python, this is how it looks like. So we have tag filter. This is where we're doing the hybrid search. So we're taking tags as well as the embedding and combining them to go and perform this similarity search. And what we're passing as a parameter is the vector embedding for the user. So remember, we say we have products, they're categorized, as well as we have the user preferences, which are unique. This is the changing part, right? This is the predicate of the query. So we're passing that along for bulky search to perform the query for us. And the return, so this is doing like a select, right? For the SQL folks, we're taking the ID back, the name, price, rating, and sorting them. Okay, so let's talk a little bit about some concepts for vectors. So the idea is that you have the products existing in this high-dimensional vector space that we can find similar items and cluster them together. The cosine similarity, it's a very simple distance between two vectors that allows us to identify how close they are, right? So if you think about a two-dimensional graph, you have vectors positioned in the x and y axis. So the cosine is just the angle that those two vectors are distant. The HNSW, or hierarchical navigable small world, it's a lot more complex. This one uses a layer-based approach that allows you to start a query and find elements on the set and then navigate through all different layers, reducing the amount of elements as you go down, right? So this is what really powers bulky search to allow you for sub 10 millisecond searches, and what's really useful for us, right? The real-time applications do require this. There's many other vector databases that are this-based, pgvector, OpenSearch, a bunch of other ones, right? But they fail to, one, provide low latency, or two, provide accuracy, which in this case for vectors is called recall, right? That's the term that they use. And in this case, we're doing also not just the similarity search, but we're also doing the tag, which is the hybrid approach. Something very important to consider is the relevance. So how wide do we want our set to be, or from the response, or how relevant or diverse, right? So there is some math that goes on down here that allows us to filter the results and provide the most accurate response for the users. Yep, so let's go probably into the detail here with the persona. I have two different users with different interests, right? So the interest is what's I'm gonna add as well as to the bio to provide that semantic or meaningful search result. So let's go back probably a little bit to the code so we can see what's going on. 1 second. A little bit more. Can you see that well in the back? No, a little bit more? Good? All right. Let's clear this up. Okay, this is the bulky monitor. I'm on the bulky CLI. And we're going to see first, let's see, we're going to log out and log back in. All right, let's see what happened. So there's a bunch of queries going on behind. All right, so what we're doing here is getting the details of the user, that in this case, we have said that we're using JSON for the user, and in the case of the products, we're using hashes. So we are also looking at all the different cache items. For example, for a given product, if this user has seen it, in this case, they did not, right? So what we did is we went and called the LLM behind the scenes and stored a product description for this user. So all of this is just to load that page, right? So as you can see, all of this weird binary data, it's the embedding, right? So what we're doing is storing the embedding of the user as bytes. That this is the numerical representation of the user's profile. So let's actually go and see that. Right. So let's see. I found this user. This is of type JSON. So I can do JSON.get the user. I'm we're going to see the root, right? So all of this is the data belonging to this particular user, where we have the ID, the name, the bio, and purchase history right here, right? And everything else is the embedding. So the embedding is the result of, like I said, the computation that we're doing with a model that is particularly good at this, and it's giving me all these array of numeric values to represent the user bio as well as the purchase history. If we do the same for the products, oh, too many. Let's take one of these and see the details. Sorry, I was cheating. I already know it's a hash, but let's take a look. It is a hash, so I can do hgetAll. And we can see that it's a different structure, right? So in this case, bulky CLI does give me a numerical list of values. The first one being the embedding as well. So it's the numerical representation of the product description, as well as the category and the tag, etc. Right? So we have the link for the image, the name, etc. So these are all the different items that are the components. But now let's take a look at the search. So if we go back to the monitor and I perform a search, let's go back to the headphones. So this where do you go? There you go. This is the FT search command that happened. So this is what we're doing. We're taking this index of products and providing that we want to get the 25K nearest neighbors, right? So 25 nearest neighbors, and providing the user vector. Like I said, this is the predicate. This is kind of the word user like, right? And we're giving this whole vector of items, and we want the ID as well as the, yeah, I think we're just returning IDs, right? So with the IDs, we're able to go and fetch based on the result that we were given, we get the different products as well. But this is what allows us to assemble this result set, right? Right? Awesome. So this is pretty much what allows us to enable this personalization pipeline, where we're converting the VION preferences to vectors and then find products that are similar to those embeddings, providing that context filtering and doing that relevant sorting with the MMR algorithm that I showed you before. So sessions as well, we're taking advantage of the Flask application. So if we go to the app, like I said, this is a Flask, and then we're importing this session item. So we're taking advantage of that as well to store all of the items. As you can see, this is a single app running locally, yet I'm still able to have two different browsers with specific users providing them similar results. We saw the cache as well, right? So if we see this product, for example, this is user 102, and this is product 870. So let's go on trying to find that LLM cache. Right? So somewhere here, yep, we're trying to see if this cache key exists. That's LLM underscore cache, and then we have the user pattern, which is the ID is 102, the product 67 in this case. So this one was 870. So it's got to be somewhere here. But what we're doing is, as you can see, we're not doing any sets, right? So that means that for these products that we're displaying, we're no longer going to the backend, which in this case is the LLM. So we're saving on latency. So instead of taking 2 seconds, like it will, like let's say I'm gonna get a different product. Yeah, it's taking more than 2 seconds probably. And then it's storing the result, right? So once we have the result from the LLM, we save it back. So we're saving on tokens to go and perform the query first, and then once we get the response back, that's also tokens that we usually will have to pay. And more importantly, for the user experience, once we have the result set, this is ridiculously fast, right? So that's kind of the whole point. Valkey will give you back that result set under a millisecond. So different, this is somewhat simpler. We're just using a string for this purpose, and it's allowing us to have this real-time feel as well as code saving mechanism for the GenAI app. Okay, so in this case, this is kind of the gist of how the sessions are being used. We're storing the user, how many items they have on the cart, the total, etc., as well as we can also have a list of items to see, for example, the purchase history. And more importantly, sessions usually have to expire, right? So we need to be frugal about the usage of memory because we don't want to keep things forever. We want to keep them as long as they're useful, but no longer. So that's something super important to consider when using Valkey. It's think about how long you want to keep things in memory that are still relevant, right? They're not stale, but they are also not there forever, so you don't overpay because RAM is more expensive than disk. The main idea, super fast access, right? You can always do this with database, a disk-based database. That's actually super, super common. Every time that I hear, well, we're using X or Y commercial database for sessions, I'm like, oh my gosh, like, if you don't want to, you don't have anywhere to throw your money, give it to me, because it gets really expensive. The atomic cleanup, right? That happens behind the scenes. If you were on the previous session, Rang was talking about how they have implemented this self cleanup that is proactive. Um, and that's also extremely useful to have that by default. You don't have to do it. Many other disk-based database don't do this by default. They, whenever you do query things that are that have expired, they won't give them back to you, but they're still sitting there taking space on disk. And they do have a vacuum system that happens behind the scenes whenever, right? So this allows you to also have extreme scalability. Who here have ever used any sticky sessions? No? Sticky sessions? Yeah. So this was the way to do this 20 plus years ago, right? So most web servers had a local session store. So for every application server, you needed to have a session storage locally that was actually in memory, but it was done by the web server. So what happens when that server goes down? Your whole experience goes down as well. So if you're a user, that server dies, right? So your proxy has to be aware of where you're supposed to be going, or you have to be cookie driven. So in that case, it would be like, okay, there's 10 servers. Robert's going to go to server 1. Dimitri's going to go to server 7. So if something happens to that server and you have a long process, like you spend hours sometimes looking for a product that you like, and then suddenly that's gone, right? Imagine doing your taxes as well. In the US, we take like days doing taxes. So that's extremely painful to have to spend hours and hours filling out a 45 page document that suddenly is gone, right? So what allows you to do this is that this distributed session store, as well as Valkey, it allows you to have replication as well. So, okay, I think I went ahead this. I show you how we're doing the caching. So by using this key pattern to store elements retrieved from the LLM, we're taking advantage of the built-in caching mechanism, which is kind of the most common use case for Valkey. Caching is kind of the quintessential and the main use case for any in-memory store. But the whole point here is being meaningful about the key naming, right? So you have to have certain pattern that is structured, and it makes sense for your whole team. This is how we storing the details, as well as having a backup for the description, that generation that is happening on this behind the scenes. And like I said, TTLs, right? So that's super important to keep in mind for how long you want to keep things in memory. The benefits, definitely the most important one is latency, like giving the users a better experience as well as the cost reduction. We all have cost pressure from leadership, right? They always want to shave cost and make sense, right? Like you want to make the business more profitable. And that scalability and reliability that I was talking about, reliability is actually often overseen when talking about caching or session stores or any place where in-memory stores come in place. Because think about it, if you don't have a cache, remember what happens every time that a big website goes down. There's a saying in computer science, right? It's not DNS, yes, it is DNS. It's always DNS. So DNS is kind of the top level caching system that we all use. You go to website.com, and then the first thing that you do is hit your local cache for your DNS. And then that goes to the next, to your router, and the router goes to the next router, right? So that's how kind of the internet works. So imagine that goes from all the way from the DNS to microchips, right? So the processors have an L1, L2 cache as well. Some of the important things is keep track of how many times are you hitting the cache, right? This is super important to have in your backend. If you don't know like what's happening, how many times are you hitting the cache or not, if you even have to cache things, for example, for the LLMs, if it's a one-off, you may not want to do it, or you may not even want to do those personalized descriptions, right? You may want to do it until the second, third time that the user has gone to that product. That's when you say, oh, yeah, they're actually interested. So it's better off to give them a description or send an email to them, right? This is, as you saw, the cache warming on the demo. I went to a product and then I clicked on or added on the URL a product that I didn't have. So the way that the application is working, we're doing this behind the scenes. It's like, oh, we don't have the data. We're going to go to the backend through a WebSocket and then do that request and do that pre-warming of the cache. So that's also super important for systems that do require to have a fresh cache all the time. Imagine going to your favorite e-commerce website and just wouldn't load because it's going to the DSpace database, right? These are some of the metrics, some performance characteristics. The whole concept of having an in-memory store is that it's extremely fast. Most of the O-of-1 operations are under a millisecond, and then in the case of the vector search functionality, it is the fastest vector database, but it's still going to be, I don't know, between 1, 2, up to under 10 milliseconds. And yeah, in the case of the Bloom filters, we saw how we were keeping track of the products that the user has seen. This is a metric that I was able to pull up, which is the memory usage. So we are able, in this case, for a random number of users, that they can see up to 10K products. Let's say that's the max of what we want to track. It's about 80 gigabytes. By using Bloom filters, we get almost 99% memory reduction. Yeah, and we're able to play around. If we need more accuracy, then we can say, okay, if you want less than 1% of errors, you can go to 0.1%. Of course, that's going to use a little bit more memory. Right? I think we went through all of this. This is just for scalability. Use bulky cluster all the time, even if you have a single chart. And then for the local development, we have a container. That's in pretty much the way that this whole thing is working. We have valkey-bundle running on my local. We have tiny Olama running on my local. And that's how we are able to get all of this working super straightforward. Yeah, key takeaways. It's built for real-time applications, right? It's not meant for everything. The idea is that you want to use bulky whenever you have performance, cost, latency issues, or you want to increase reliability. What is not good for strong consistency guarantees, complex queries, right? We saw the kind of searches that we can perform. We can do hybrid, but we cannot do full text search, for example. And we don't have long-term analytical data warehousing kind of use cases. Yeah, I think that's it for me. This whole demo, it's built upon a bulky search demo that somebody from Google did, and then I just enhanced it. So thank you so much. Please go to the blog, download the code, and I'm open for questions. You want to take this?
Any questions?
I'm not that good. Come on.
Wait.
Available. Sorry, I'm just curious more about the valkey search demo. Is there a lot of overlap between what you did and that? Because that is the
I built upon that. Yeah. So this.
cool.
The
Can I get access to the repo where your code is?
Yep.
Please.
Yeah.
Yes, because that's what I'm actually trying to kind of like.
Yeah. So
experiment
there's.
with as a valkey search.
Yeah, there's a bulky search demo that we're going to publish on the bulky.io organization. And what I did is expanded using JSON and using Bloom. And then I'm going to add the LDAP as well.
Thank you. Yes, definitely want to dig into the code.
Any other questions? Can I use this for AI workloads?
This was all AI. You missed it, but
That's true. I walked in 5 minutes before the end.
yeah, essentially, what
Can I make this more agentic? That seems like a more relevant question. You don't have to answer that. I'm just filling time.
This in this case is for vector similarity semantic search use cases. So what we're doing is finding, depending on the user, relevant results, right? Of course, you can do it agentically. You can have, let's say, you want to run an application or you want to create an application that does go to multiple sources to go and find relevant results for you. Let's say you were trying to find a car, right? You want to buy a car. You don't want to go to 15 different brands and dealers, right? Like you can just create an agent that does that.
Any other questions? Oh,
Thanks for showing this. Very interesting. One question though: you created the index for the products for the search.
Yep.
But I assume that you need to add every product individually to that index.
Correct.
Is that something that I missed, or?
Yeah, so essentially, as we are populating the catalog, we're generating the embedding, right? So I showed like we're taking the product details, the brand and price, etc. We're creating an embedding, right? So that with one of the embedding models, right? There's different models. One is for embedding, and the one is for searching, or for the descriptions. This is the NLP one. The embedding, it's done at the product catalog upload, right? So that takes like a few minutes. I didn't do it, but yeah, essentially I did it beforehand, right?
Okay.
So,
Okay.
Yep.
Thanks.
all right. Oh, I think it's almost time for lunch. So if no, you have a question? Perfect. Kyle was staring at me, and now he's not, so we can ask more questions.
We have 8 minutes,
Hi,
but you're hungry.
I have a question regarding the Bloom filters. Like, how do you invalidate or rebuild for a particular user? Or
Yeah, well, yeah, you will have to play with the TTL, right? So you want to keep track of however many items you want for a certain period of time. Yeah, because with Bloom, there is no removing. You can only add, but you cannot remove.
yeah, exactly. Okay.
Yeah, for that, there's cuckoo filters, which is similar, and you can remove. They use a little bit more memory, but if you're interested, there's a GitHub discussion about that. So,
Thank you.
Just to clarify, you don't have 8 more minutes. You have -3 minutes.
I thought it was until noon, but thank you.
10,
I'm going to let you go.
That's why I said lunch is ready, I think. So, if there's no other questions, I think it's time for lunch. So folks can go grab that. And also, they can always go talk to Roberto more during lunch.
Yeah, you can come to the workshop afterwards, after
Exactly.
lunch. Thank you.